So the last bit in this topic is how force can cause turning effect and how we measure what this is called, which is called a moment. So very simply, any force applied to an object which is attached to a pivot, so a non-moving part, will cause a turning force. So we see that here we've got a nut which we want to rotate, so it rotates about the center. If we try and turn a nut just by holding it with our fingers, it's very, very hard to do. If we put a span around it and apply the force further away, it's easier to turn the nut. This is a general principle that the further away the force is from the pivot, the lower the force that you need to apply, but you do need to turn it for a longer distance. So we measure this using the idea of the moment. So a moment is a turning force caused when a force is applied to an object connected to a pivot. Okay, and we measure it simply as the moment equals the force times the distance from the pivot. Okay, so it's easy to understand on a idea like this. Let's just see the units. So the units of force are newtons, units of distance are in meters, so the units of the moments are newton meters. So here this would be the pivot, this would be the force, so the weight of the person acting downwards, and so the distance between them would just be this distance here. This would be the weight of this person, and so the distance would be greater here to here. So an example is given here. So we've got a weight of 20 newtons, we've got a distance of 1 meter, so 20 times 1 is 20 newton meters. Equally on this side, we've now got a weight of 10 newtons, but a distance of 2 meters, and therefore the moment in this case is 20 newton meters. So in this case we've got a moment acting downwards on the right and downwards on the left, and because these moments are the same, 20 newton meters in both cases, then we have a nice balanced situation. So anytime you've been on a seesaw, perhaps with your parents or older brother or sister, if you wanted to be balanced, then the heavier person had to move closer in. If you both sat at the same distance, then the heavier person sits on the ground, you sit up in the air, and nothing happens. So that's how we measure moments. So the law of moments basically says something along the lines of for a balanced situation like this one here, and we give this the fancy name of an equilibrium situation. The moments on either side of the pivot must be equal. Okay, so we've got 20 newton meters on this side, 20 newton meters on this side, so the seesaw in this case doesn't move, it's balanced. If we are going to give these the formal name, if you consider which way this weight is moving, and this side of the seesaw is moving, it moves downwards, and if it was to rotate all the way around the pivot, it would rotate in this direction. So this is the clockwise moment, and this one goes down, but then it would spin around that way. So this side is the anti-clockwise moment. So the more formal way of describing the law of moments is to say the clockwise moment equals the anti-clockwise moment. So the last bit, state and explain laws of moments. So we've done that, and then explain how objects tip over. So the last bit is how objects tip over. So as we talked about earlier, when we're looking at how weight acts on an object, the easiest way to work that out is to talk about the center of mass, or the center of gravity. So for a regular object, it's very easy. We say that all of the weight of an object acts from the geometric center of it and acts downwards. So if you've got a circle, that'll act at the center of the circle, act downwards. If you've got a triangle, nice equilateral triangle, it'll act at the center. So this is our center of the gravity. With more complex objects, it's slightly trickier to find it. You can do this relatively easily, but it's not always so obvious. But for the idea of just when objects tip over, very simply, if the center of gravity is somewhere between the edge of the object, then the object won't tip over. So here we've got our center of gravity is acting within the edge of the object, so that's one edge of the object, that's another edge of the object. So that's your edge there, that's your edge there. Here you've got nice edges, and here you've got nice edges. So the center of gravity is acting within the footprint of that object, so that object is nice and stable, it won't tip over. If you take this object, and let's take a square again as another example, and take our square and tip it a little bit, then our center of gravity is still acting within the edge of the object. If we tip it a little bit further, our center of gravity is just acting just on the edge there, so it's just acting at that point there. If we tip it even further, our center of gravity is now acting over our tipping point. So this is our tipping point here, this is our tipping point here, this is basically our pivot. If we let go of our square, it's now going to drop down, so this side will drop. Here it'll just about balance, but a little bit of wind will knock it one way or the other. Here, this side, it will fall down this way and it'll fall over. So a car, for example, its center of gravity is going to act between the two wheels. If you tip the car a little bit, the center of gravity is acting between this pivot, and so when you let go of the car, it will drop down, it will come back and land on its two wheels. If the center of gravity is now just beyond the tipping point of that car, then that car is going to flip over and end up on its side. This one is just going to drop back down. So that would be when a car tips over, when the center of gravity acts beyond the pivot, or one side of the other pivot, then it will fall over. Okay, so that's all of P2 chapter 3, so it's quite a bit in there. So just go through that. BBC Butts Eyes, Caboodle, Sam Learning, your notes, revision guides, all those things, and just do some good revision on those subjects.